Hello everyone and welcome back to PC Retro Programmer. In the past few videos in this series we've been working towards cycle accurate graphics effects for the original IBM CGA graphics card that was used with the original IBM PC. And this is a long process, but we've made considerable progress. The most important thing, of course, is to get the machine completely silent so that there are no interruptions to our cycle accurate timing. So we have a little program that demonstrates this. It has interrupts turned off and dynamic RAM refresh turned off. Those are the two main things that can interrupt our code and cause disturbances. So what we're doing here is we're changing the background color to red, but instead of the whole screen going red, we're just seeing a very small line. And that's because we're turning the background color to red and then immediately back to black again. Now, of course, if you didn't do this at exactly the same point every frame, you'd see this little red bar moving about all over the place. And, of course, if the machine itself was not completely silent, there'd also be interruptions that would cause movement. We're even putting the CPU into hold mode at the end of each frame and then waking it up with a timer interrupt at exactly the same point every frame and then doing the background color change. And as you can see, it's completely stable. In the previous video, we even got it so that we could mash keys on the keyboard and they wouldn't generate interrupts that would mess things up, but we can still press the Q key to go back to DOS. And there are still a couple of things that we have remaining to deal with. So the first of these is that every time I run this program, it puts the background color change in a slightly different place. You can see that it's never exactly the same location. And so that's something we're going to need to fix in a later video. In today's video, there's one more issue that I'd actually completely forgotten about that we still haven't dealt with. When I go back to DOS here, I'm using IBM PC, an emulator. There's no problem. If I run another program or a dir command, everything works just fine. But on genuine hardware, what we get is a parity error. And the reason for this is we have dynamic RAM refresh turned off, so the contents of system RAM decay over time and become corrupted. And whenever we read those memory locations, the machine detects the corrupted values and the BIOS halts the machine with an error message saying there's been a parity error. And the only way out of that is a hard reboot. I'd have to pretty much switch my machine off and on again because I don't even have a reset button. And so this is really a problem when developing code. It also takes a long time for my machine to boot. So we don't want that to occur. Now I can't just turn the automatic dynamic RAM refresh back on and get the DMA controller to handle it as normal, otherwise the jitter will come back. So we need to do the dynamic RAM refresh ourselves manually. And it turns out that if you just read the system RAM in a certain way, then that has the same effect as dynamic RAM refresh. But there are lots of open questions about this. How often do you really need to do it? And does it matter whether I do it on a regular schedule, or can I bundle the refreshes and do them all at a certain point in the frame? So these are questions that I actually don't know the answers to myself. I have done some experiments, but I really don't know exactly what the limits are. So in today's video, we're going to try and figure that out together, and we'll write some code that will allow us to return to DOS on a real machine without any parity errors whatsoever. Now, the first question that I need to answer is precisely how much memory do I need to keep alive using manual dynamic RAM refresh. And for this, I need to know how much memory DOS takes up. It's surprisingly difficult to find this information online, or even where DOS gets loaded or where it will load my program. What I've been able to determine is that at the very beginning of memory is the interrupt vector table, and following that is the BIOS data area, which the BIOS uses to store various bits and pieces of information about the hardware and some variables that it uses as the machine is running. And then following that is where DOS is loaded in memory, and then immediately after that is where my program will get run. So it's all at the beginning of memory. Now, I vaguely recall that DOS also puts some stuff later in memory, and that may actually be the case, but from what I can tell, this is just the transient portion of command com. And I don't think that will be relevant, and the reason is that, as far as I'm aware, this is designed to be overwritten. So basically, if your program wipes that out, so long as DOS has access to a copy of command com on disk that it can get at, when your program is finished, it will just reload the transient portion of command com and everything will be fine. So we can exclude that from our calculations. Now, there is a website that claims to give information about how much space DOS takes up, but unfortunately the values don't match what I get, and probably because of this transient portion that we want to exclude. Now, I thought I could just run mem.com, which is a DOS utility that tells you about memory usage, but the problem is I don't have that in my version of DOS. That might be a good thing, as I'll explain a little bit later. Another solution might be to run debug.com, load my program, and I'll be able to see where it's loaded in memory. But unfortunately, that means that debug.com will be in memory, and that also takes up space. So I decided to write my own code for this. Now, I won't go through this in detail because the main thing in this program is just a routine for printing a hexadecimal value on the screen. And we've already seen how to do that in a previous video on writing an interrupt-based timer. So basically it just takes a 16-bit value in one of the registers, in this case the DX register, splits it up into 4 hexadecimal characters, converts them into ASCII. There's a little bit of arithmetic you can see down below for doing that, and then prints each of those ASCII characters to the screen using the BIOS teletype routine, which is a routine offered by interrupt 10H. This will work in text and graphics mode, by the way, which is really nice. Once it's printed all 4 of the characters in a loop, then it just returns to the beginning of the line, again with a call to the teletype routine with character 13. And that's basically all there is to it. The main program is even simpler. It just takes the code segment address of my program, in other words where it's loaded in memory, and puts that into the DX register and calls that print routine. And then it just waits for a key, and when that happens it returns to DOS. So very straightforward program. When we run this, it's going to give us the segment address of our program, and if we multiply that by 16 we'll get the actual physical address in RAM where the program is loaded. Add to that the length of my program, and then I know exactly how much memory I have to maintain. So let's run this and see what address we get. You'll have to excuse the noise. This is running on my original IBM XT, and yeah, the hard drives are really that loud. So first thing I'm going to do is run the DOS version command, and it says that this is IBM PC DOS version 3.3. So this is not MS-DOS, but very similar of course, and it's an early version and it doesn't use very much RAM. In addition to that, I've got no drivers loaded here whatsoever, so configsys is empty, and in AutoExecBat I have just a path statement, so there's not even a mouse driver here. And so let's run our DOS mem program and see what segment address it loads at, and it says OC84. And this is well within the first 64K bank of RAM. The second bank would start at 1000, and so this is great. It means that DOS plus our program, if it's kept small enough, will all fit into 64K, and so that's the only memory that we need to keep alive. That's what we're going to do in today's video. Now, this is not a typical situation, of course. Later versions of DOS used much more memory, and if you've got other drivers loaded, then that's going to start using more. In fact, on my PC, on my laptop, the way I have it set up there with the version of DOS that it uses and the drivers that it loads, I think I get a segment address of something like 2440, so already well into the third 64K bank of RAM. Now, there's nothing wrong with that, of course, it's just how I want it set up, but we're going to work with something much more minimal today. Now, in fact, the only information I can find online about DOS memory usage is on the CTRL-ALT-REES website, and obviously that's a high-resolution photograph of him on the left here. Now he actually gives MS-DOS and PC-DOS information, but I'll just show the PC-DOS stuff here, and there's a link in the description if you want to check out the whole article online. For version 3.3 he gives about 55 kilobytes. If you do the calculation based on the value that I got, it's about 51k, and perhaps the difference is either mem.com or the transient portion of command.com or something like that. But the interesting thing here is that if I'd used any later version of DOS, I would have been already well past the end of that first 64k bank of RAM, and so I'd have to maintain two 64k banks. So I'm actually really lucky that the version of DOS that I'm using is so early, and it looks like if I wanted to have even more memory, I could just use a much earlier version of DOS. So that's really interesting information. The code for this episode is in refresh.asm, which you can find at the link in the description. And the main difference between this and the previous video is two very short routines. And actually the puzzle is going to be why this works rather than how. So the idea is really simple in principle. We just need to keep that first 64 kilobytes of RAM alive. This is where DOS and our program reside, and the easy way to keep RAM alive when dynamic RAM refresh is off is to read the contents. This energizes all the little cells inside the chips and keeps the contents intact. Now, of course, reading 64 kilobytes of RAM over and over would be very expensive, but fortunately these chips are laid out in little rectangular arrays internally with rows and columns, and it's actually sufficient to just energize each of the rows in turn, and that will keep the whole chip alive. Now, the way it works is that on my machine, that first 64 kilobyte bank consists of 9 64 kilobit chips. There are 9 because one is set aside for parity, and the other 8 correspond to each of the bit positions within a byte. So every time you access a byte of memory, all of the chips are accessed simultaneously. So the only question remaining is what pattern of bytes do I need to access in order to hit each of the 256 rows that exist in the chips in my machine? And the answer is that I just need to access any 256 consecutive bytes, and that will hit all the rows. Now, the fastest way to read 256 consecutive bytes is to execute some code. After all, the CPU has to read code in from memory in order to execute it. So I just need 256 bytes of code that I run often enough to keep the chips alive. And that's what this little routine here does. So it's just 256 no-op instructions in a row, and each of those is 1 byte of machine code. Now, I didn't want to write all those no-ops out by hand, so I just used a little macro here to do that. It just tells the assembler to repeat the following code 256 times, and there's the end of macro there. And then I just do a return instruction, and if I run this often enough, that should do the trick. The question is, how often should I do it? Well, let's scroll down to our frame loop down here. For the time being, I'm just going to call this once per frame at the end of the frame. Now, I might need to do it more often than that, and it also might be that I need to intersperse these throughout the frame. Maybe I can't get away with just putting them all at the end of the frame loop. We'll just have to find that out. Now, there's one other thing we need to take care of, and that's the rest of memory, which we've just let decay. If we go back to DOS, then if we load a large enough program, it's going to start reading memory past that first 64K, and this will all be messed up, and we'll get parity errors. Even if we do a soft reboot, basically the machine will do a memory check, and it will realize that the parity bits don't line up with the rest of the values in RAM, and it's going to halt the machine. So the way we get around this is by zeroing all the rest of RAM. There's nothing of interest in there, so it doesn't matter to overwrite it. And writing to RAM doesn't actually cause parity errors. And setting the values to 0 has the effect of also resetting the parity bits as well to correct values. And so the machine will be none the wiser. We'll just restart dynamic RAM refresh and it will never know that the values have decayed. So this is what we do at the end of the program here. I have a little routine that zeroes out all the rest of memory. It starts at the second bank of 64K, which has segment address 1000, put that in the ES segment register, and I will start at offset 0. I'm going to be writing words of 0 into the RAM, and they're going to be 15 blocks of 64K. In my machine I have 640K in total. We've already dealt with the first block of 64K, so there's just 15 blocks left. Now this will work on other machines as well. It doesn't matter if you write out to RAM that doesn't actually exist. This is completely harmless. So basically this loop will run 15 times, and each 64 kilobyte block consists of 32K words. So I just repeat this STOSW instruction that many times, and then move on to the next segment and do this 15 times, and that's all I need to do. Straight back to DOS. So let's try this out and see if it works. Well, here we go, and I did need to make one change. I'd actually forgotten to turn DRAM refresh back on. I fixed that issue in the repository as well. I won't show the code because it's pretty much the same as turning DRAM refresh off, which we already showed on the channel, except that you put the PIT timer 1 back into mode 2 and you set the count back to 18 PIT cycles. And this is how often the DMA controller needs a pulse from the PIT to do the ordinary DRAM refresh. Now I'm letting this run deliberately for quite a while here. Ordinarily the memory decay would start within a few milliseconds, but if I were doing partial DRAM refresh and just not quite doing it often enough, it would actually take quite a while before it would decay completely and you'd actually see problems. But this is plenty, so let's just mash some keys, make sure that works. All seems fine, and I should be able to press Q and go to DOS. And it takes a while to zero all that memory, but everything's fine there. I'll do a DIR. Now, of course, this is only going to tell us about the memory that DOS is in, that first 64K bank. So the real test will be to go into DOS debug, and what we can do from there is dump memory at various locations. So if I just do D, it'll dump. You can see that this is already in the second 64K bank. And I can also dump from other banks as well. So let's just do some random address here, and that's all fine. And I could do one, much later in RAM. It's not going to make any difference. And that's all fine as well. So it is working, and the only question remaining now is why? What I haven't told you so far is that in no way should this work. The DRAM should require refresh much more often than we're doing it, and yet somehow this is actually working. So let's take a look at the details. Now the way this works is that on the original IBM PC there were a couple of different memory configurations. On the earlier motherboards they used lots of 4116 chips, which are 16 kilobits, and on the later boards they used these 4164 chips, which are 64 kilobits. Now the smaller chips had fewer rows, just 128 instead of 256. You can see on these later chips they had 8 address pins, and so what you'd do is you put the row address in first, so you had 256 different rows you could access, and then you'd put the column address in, and there'd be 256 of those, and that would give you access to 65,536 cells. But on the earlier chips there were fewer rows, but of course the chips are smaller, so you actually needed 4 times as many banks. So in that first 64 kilobytes of memory there are actually 4 banks instead of 1. So overall, on the earlier PCs you actually had to energize twice as many rows as on the later ones. Now, in my XT, which I've been using today, the first few banks also use these 4164 chips, in fact specifically these Samsung ones. And in the later banks, it actually uses larger chips, 256 kilobit ones, the 41256s. Now, those only need DRAM refresh half as often, but they have twice as many rows. This is irrelevant though, because those are the chips that we're just letting decay, and I've actually checked and triple checked that the first bank on this machine, bank 0, is clearly labelled on the motherboard, and it definitely has 4164 chips in it. Now this is surprising because these, and the 4116s as well by the way, require refresh every 2 milliseconds. And that's 8 times per frame, and we're currently only doing it once per frame, so 8 times out of spec. And this is particularly surprising to me because I've previously done experiments to see how far you can push these out of spec by slowly increasing the cycle count that's used for the normal DRAM refresh using the DMA controller. And little bit by little bit, push them out of spec to see how far you can go. And the answer is, if you do the test really carefully, not very far. So why is it that we're getting away with something so far out of spec? I don't know the answer to this. I've asked a few people and it's a real head scratcher. Maybe there's something different about the way the DMA controller does it. A much shorter pulse, for example, or it just doesn't energize the chips as far. I really don't have any idea whatsoever. If you've got an idea, let us know in the comments below. Now, I don't think that it can be a bug in my code. I've rewritten the code multiple times, and I've actually tested it over many weeks with very long runs and had no issues at all. I got so suspicious of it that I actually put in additional code at the end of my program to read every address in memory before returning to DOS to deliberately trigger any parity errors. And nothing. It works just fine. So at this point I have no explanation for this, but if this works more widely, then it's a really great technique. It's just a little over 1,000 cycles to do all the DRAM refresh we want every frame, and this is just over 3 scan lines, which is easy to hide in the vertical retrace period, for example. Now, if there are viewers out there that have these chips in their machine, it'd be very interesting to know whether this code works on your machine. Let us know in the comments below. I've actually run this on my other PC, which is a later PC that also uses these 4164s, and it works just fine. Now, I can't test an earlier PC with the 4116s, and I suspect those earlier chips are much more finicky. And in any case, our code doesn't currently try to access rows in all 4 banks in that first 64K, so it wouldn't work anyway. But if this does work on other machines with these chips, then we should be able to do some really cool effects. We've got plenty of time left to do lots of stuff in the frame. So all things being equal, that's what we're going to do in the subsequent videos. To finish off, I decided to run a little experiment to try and back up the claim that I made earlier, that if you take the RAM just a little bit out of spec, using the ordinary method, which is to increase the PIT cycle count for the DMA controller, then you don't have to go very far out of spec before you start getting parity errors. So this program basically just modifies the cycle count in the PIT. This example here just changes it to 72, which would be 4 times out of spec, and then just exits to DOS. And later on I added some additional code to this to actually try and trigger a parity error by reading RAM from other banks. And I ran this on my PC and my XT. Now on my XT, I got to the point where I could actually take the chips 1,000 times out of spec before I actually started to see parity errors. This is just inconceivable. I don't really understand how that's possible. And I did this on my PC, and it was even further than 1,000 times out of spec. I just gave up in the end, getting it to give a parity error. So basically, what I have is a past experience of having checked this using a different program and finding that if you take it even a little bit out of spec, eventually it will parity error. But today, having the experience where I can take it wildly out of spec and not having parity error. So I don't have an explanation for this. It seems that there's some other criteria that are involved in generating parity errors, and we don't know what they are at the moment. Maybe it's to do with the contents of RAM, or maybe it's to do with how warm the machine is. I really don't know. If you have any ideas, let us know in the comments below, but at the moment this whole thing remains quite a bit of a mystery to me.